So here linear damping we are having. So the equation of motion with a linear damping will be mx double dot plus cx dot plus kx equal to, let us say, ft. So now we use the non-dimensionalization and we got this following form: x double dot plus twice zeta omega n x dot plus omega n square x equal to n by n. So this is the form we got. Okay. Now our task is to find out the solution of this system. So again, as usual, we use the Laplace transform technique. Now here, if you consider the Laplace transformation of both the sides, that means Laplace transformation of x double dot t, this will be xs dot, and Laplace transform of x dot t, at 0. Okay. So in that case, if you take the Laplace transform both sides, then you will get a square xs plus s So that is we are getting, and from this I should be able to write down xs as s x naught plus x dot naught actually I should have written small f there, so that small f, so this becomes capital Fs, and this times m. So that is the result we will get. So this is the Laplace transform of the response. Now we have to find out, then the next step will be to get the function, that means xt, which will be the inverse Laplace transform of x s, and for that so we'll have xs equal to here sx0 s plus twice zeta omega n square, zeta omega n square plus 1 minus zeta square omega n square, this plus fs by m times 1 divided by right? Okay. So I have here the Laplace transform the inverse Laplace transform of this quantity. Okay, so what will be the inverse Laplace transform of this function denominator? So what will be the inverse Laplace transform of this thing? Can anyone tell? So okay, so um, now here we have two cases. Okay, so I have to find out the inverse Laplace transform because this denominator is very important. Numerator we have x and the denominator we have this thing x dot 0. So denominator is very important. Here also the same denominator comes. Now when we want to get the Laplace inverse Laplace transform of this quantity, we will have to be very careful. Okay, because there will be now two separate cases. Case 1, when zeta is greater than equal to 1, maybe we consider greater than 1, equal to 1, equal to 1, and case 3, zeta less than 1. So we'll consider these separate cases. Okay, and you see this part actually the part of this response here because of the inverse Laplace transform of this quantity. This is nothing but the response with no forcing, and the other part of this response is the response of the system with forcing only and zero initial condition. So again, just like all the linear systems, we have a clear-cut separation of the response into two parts. One is the zero force response and another is the zero initial condition response due to only the force. So this is the way to separate out. Now let us see what happens when we consider uh, this quantity, this s plus zeta. I think we please check. So this part, this was x dot. So
I think he means of this x
can,
dot,
can,
sir.
can, can you please tell me the numerator of this function? I'm not. I think I made a mistake because I did not
Two
consider.
zeta omega n x naught.
Yeah,
Yes, 2 zeta omega.
2 zeta omega naught omega n x naught.
x naught,
X0.
right? X naught, and this is actually
X0, sir. X0. X0.
x zero. S square. Yeah. So s x zero. This one will be.
X0.
No, is this correct?
Yes, sir.
Is this fine?
Yes,
Okay.
sir.
So now let us say what will happen to this particular thing. Let us consider case zeta greater than 1. Greater than 1. Then what will happen? This denominator is zeta greater than 1. So if I write down this quantity as omega d square, so if I consider this as omega d square, that means what I am writing down, omega d is omega n times, let us say, under root 1 minus zeta square. Suppose this I write down, then the denominator, this becomes 1 by 1 plus zeta omega n, s plus zeta omega n square plus or minus omega d square, right? This will be omega d square minus, and then this will become, just let me that way. So So this will be S plus zeta omega plus omega d omega d. Okay, so that will happen. Okay, and then here this part will be 1 by 2 omega d, and there will be a negative sign. So this will be minus here and this plus here. Now please check. That is so. Okay.
Sir, you will replace it by omega.
Yeah. Yes, omega
You
n.
replace.
So this
Sir, you
will be
replaced 1 minus zeta square into omega n square by omega d square, no?
omega d, right. Omega d is equal to omega n times under root 1 minus zeta square. So here actually omega d square, I should write down omega d square equal to d square times 1 minus zeta square. And since zeta equal to, okay, I should not write down this part. So let me check. Here it will be omega d square. So what will happen? Negative of this thing. So this will be zeta square minus, so this becomes actually zeta square minus 1 omega n square. Okay, let me call this as omega d star, and here, so omega d will be equal to, let me check, omega d star, omega d is equal to omega n under root square minus 1. So let us write down that. Now you can find out then the response due to the this part. There was this S, then plus twice zeta omega n twice zeta omega n x naught plus x dot naught and so on. So here this was S plus twice zeta omega n. Okay, so this twice zeta omega n x naught plus x dot naught and so on. Now you see this kind of system, here it will have the response. So response will be of what form? The response will be now in this form, that is e to the power minus
Exponential.
Zeta omega n and the response due to other thing. Okay. So here also this will be, so here this will be e to the power minus zeta omega n and so on. So this will be the response here. Now see, this part is actually, so I leave this to you, that how to get the inverse Laplace transform of this thing, but because S plus zeta omega n is appearing in the denominator in this form, so you know that the Laplace transform of, if Laplace transform of this is equal to Fs, then Laplace transform of Fs plus alpha will be equal to e to the power minus alpha Ft will be like this. So this result is known, and using this result we get that the Laplace transform of the of this response will be, the inverse Laplace transform of this particular quantity will be e to the power minus zeta omega n, and the remaining term. Okay, so S plus zeta omega n will be appearing, so there will be this kind of term will be appearing there. Okay, so this is one thing. But so here what we are getting, that for zeta greater than 1, you have a response where, sorry, this is a t term is meeting, zeta omega n t and minus zeta omega n t, these two terms are there. So because of these two terms, actually what will happen, the response will always decay. So what will happen for zeta greater than 1, we will have xt, which is only due to the zero state, that means it is not because of this part for Fs, but only for that one. This will be e to the power minus zeta omega n t, and something will be there plus e to the power minus zeta omega n t. um, it will be better if we write down, say here I took e to the power minus zeta omega n t. Maybe what we'll do, you'll write down zeta omega n1 and omega n2 here, because there will be one thing that is dx plus twice zeta omega n plus omega d prime, and if there will be s plus zeta omega n minus omega d prime. So if you consider this entire term here, so it is advisable to take not only this term but entire or both these terms. So therefore s plus, let us say s plus, this will be s plus a, and the other term will be s minus a. So you'll get e to the power minus zeta omega n 1, so omega n1, and this will be omega n2. So these are the two terms. So you just take out. I am not doing it very systematically here. What I am saying that there will be this s plus zeta omega n plus omega d prime, and there will be another term s plus omega n zeta omega n minus omega d prime. And then if I write down this as omega n1 and this as omega n2, so I'll get something like 1 by s plus omega n1, and another one is s plus omega n2. In that case, I write down this as s1 plus s plus omega n1 and omega n2. So here the response will be this thing, and the inverse Laplace of this part will contain minus zeta omega n1. Okay. Minus zeta, I write down this as omega n1, maybe I'll just consider zeta omega n1. So omega n2. So this will be the response line, and that is only for the non-zero initial condition. But for the response, for the response, that is, we have fs there, this divided by m, and this will be this times, I know that this is 1 by s plus omega n1, and this is 1 by s plus omega n2, supposing that, and there it will be omega n2 minus omega n1. So this is what we'll have. Then for this one, unity, and therefore fs. So here what we'll have here, so I'll have to consider the inverse Laplace transform of this quantity, which will be of this at least one integral form. So what I want to say is that for the forcing part, there will be one response, but for the zero initial condition response, these will actually decay exponentially with time. So what will happen if you do not have any force? Suppose say f equal to 0, then what you will get, the response will be a decaying function. So t and xt, whatever be the initial condition, it will actually decay there, either this way or this way. Okay, so eventually it will go down to 0. So this is the only the zero initial, only for unforced system. But for the forcing, actually what will happen, for the forcing, the result will not be 0, because this integral term will be appearing. So if fs is not equal to 0, then what will happen, the integral will, this integral part will be there, and there will be some kind of response. I am not going to discuss much details for this one, because this is not very important from our vibration point of view, because you see this is not a regular vibratory system. The system is called the overdamped system. So damping is so large here, that is, the system naturally it does not overdamped system, that is zeta greater than 1. Okay, so it will have, this is overdamped system. Now you have, so this is what we have. The characteristics of the overdamped system is that natural vibration, so there is natural response, that is ft equal to 0. This is decaying, it is exponentially decaying. forced response, of course, with forced response, there will be some forcing response, but because the initial condition part will decay. So if you have a forcing, then there will be two parts. One will be this part which will decay. So that is the I call free vibration, and there will be another one which will be maybe I do not know. It can persist. This is the let us say the steady state response or due to the forcing. Okay. So the forcing part will be there, but that depends upon how the forcing is applied, but the natural part, that means the initial condition part, it will decay down. So there will be actually a transient part. This transient will die down very fast. Of course, if the forcing is not persistent, that means if the force stops after some time, then eventually the vibration will stop because of the damping present there. So this is a damped system, but what we have is that there is no oscillation. That means free vibration does not exist. It will only just decay very fast to zero. So it is not actually an example of a vibrating system. Okay, because it is overdamped, so it does not actually show persistent vibration. Now the second case we'll have is that zeta is equal to 1. Zeta is equal to 1, and in that case denominator will be equal to s plus zeta. That means zeta is equal to 1, this will be equal to omega n square. And you know of this form, the inverse Laplace of this one will be, what will be that? Inverse Laplace? What will be the response? Inverse Laplace transform? What will be the inverse Laplace transform of this form?
T e to the power minus omega n
E to the power minus omega n t and
into t.
into t. Right, because t will be Laplace transform of t is equal to 1 by t square. Right? Is 1 by t square or 2 by t square? Just check, I believe it is 2 by t square, but anyway, of this form, there may be a coefficient which will be there, but what we have is that here, initially, it will decay with, it will increase in time, because when t tends to 0, so this term is very small, and this term is equal to 1, so it will increase in time little bit, and then eventually this term will actually be superseding, that is this term will be overwhelming, and then eventually it will go to 0. So this is the case where zeta equal to 1, small increase in response because, or decrease like a linear response, this is t, well t because of t, but eventually it will die down. So here the response is again not that of a vibration. So we call this response as the, or the damping as the critical damping. So critically damped system. Okay, this is the critical damping where the response is actually of this form. Again, e to the power minus omega n t, but there are not two omega n's, omega n1 and omega n2 as I had written earlier, but only a single minus omega n. But there is a time varying part, which is there is this t and this part. Of course, this will dominate after a long time, and it will eventually go to 0. All right. So this is what we are having for zeta greater than 1 and zeta equal to 1. Now let us consider the case when we have zeta is less than 1. When zeta is less than 1, you will see that when zeta is less than 1, we have s plus zeta omega n square plus here omega d square, where omega d equal to omega n under root 1 minus zeta square. So this is what we have written. And what will be the Laplace transform of this part? What will be the Laplace transform? Inverse Laplace transform of this? Inverse Laplace transform?
E power minus psi omega n t.
1 by omega d e to the power
To the power
Minus psi omega n t.
and
Sine
omega dt.
Sine omega dt. So this is the inverse of this quantity, right? So this is what we are having here. Now, of course, the initial conditions will be coming because now our xs was s plus twice zeta omega n. This was okay omega n x0 plus x dot 0. Okay. This divided by s plus zeta omega n square plus omega d square, and this part, this will be what? This will be fs by m times 1 divided by s plus zeta omega n square plus omega d square. Okay. Now what we will do, we will write down this as zeta omega n, partly we will write down here, and this here zeta omega n x0. So this is what we have to write down. Okay, zeta 2 zeta omega n I have taken because just to get the Laplace inverse of this form in a simplified manner. Now, if you get the inverse Laplace transform of this quantity, you will get xt. What will be the inverse Laplace transform of this part? This will be e to the power minus zeta omega nt x naught, and this will be what? Cosine omega dt plus 1 by omega d e to the power minus zeta omega nt, and this part x dot 0 plus zeta omega n x0 times sine omega dt. This part will come, right? This thing, because of that, this will come, and the last part will be equal to 1 by m, then omega d, right? And this will be again 0 to t gt, that is e to the power minus omega n t minus tau sine omega d t minus tau f tau d tau. So this will be the inverse Laplace transform of this quantity. Is this clear to you? You have to do it yourself. Okay. So this part is actually, so here we have this quantity, and this quantity contain this first part up to here. This contains every information of the initial condition. The other part is because of the forcing with a zero initial condition. Now here you see that we have an integral, the kind of impulse-like integral of here, where we have this e to the power minus zeta omega nt sine omega dt cos lt. Okay, so the convolution of these two integrals. So this part, this divided by m omega d, this is actually, what is that? This is the impulse response. Okay, impulse response. So if you give an impulse, just as we had given for the undamped system, if you give an impulse, there will be sudden jump in the velocity, and there is no change in the displacement. So with the sudden jump in the velocity, the response will be like that. So what will happen, that there will be sudden jump. So x naught will be 0 because this is initially static. So if you put x dot 0 at certain value, so 1 by e to the power minus zeta omega nt divided by omega d and sine omega dt. So this is the form of the response that will actually persist. Okay. So this is the impulse response. This part is the Duhamel's integral or the convolution integral, and this is what we call this within bracket we'll call the impulse response. Impulse response. Just like we had for the undamped system, this will be actually obtained if you consider this integral. You can get using the consideration that at different instants, if you give appropriate impulses and add them up, add the net effect, because this is linear system, so superposition is possible, and also it is linear time invariant system because there is no time varying component in the coefficient of this differential equation. So in that case, what will happen? You can always always use the shift in the time scale, as I have done. So this is the technique, the same technique as we did for the pre-vibration of the for the vibration of the undamped system. Just the same thing with the damping, and this will be the impulse response. So with using the impulse response at different for different impulses given at different instance of time, we'll get this particular integral. So integral is from 0 to t. Okay, because we are only considering the time up to up to a certain point. This is denoted by t. So at the function f(x)t at time t is given by this one. So we can also write this part, because if you just take out all this stuff, e to the power minus zeta and t, so what you will get that cosine omega t. Okay, so this part will be cosine omega t. I can write it down this way. This will be 1 by omega d sine omega dt. So that is what we can get that. So you see that the response here, this can be written, this part, the free vibration part can be written as, see, e to the power minus omega n t, certain terms times cosine omega t, and certain other terms times sine omega dt. So we can write it down this part as, let us say, the amplitude times cosine omega dt minus phi. Okay, where amplitude will be, where amplitude is the term corresponding to this one, x naught square plus what was that? The other term. This is 1 by omega d and zeta omega n x naught plus what was that? This is x dot, I think. Something like this, and similarly you can get the phase difference. So there will be amplitude and phase difference, but this amplitude will actually decay. Okay, this amplitude will decay. So the response without forcing, let me consider now the response without forcing and with forcing. Now what will happen to the response without forcing? The response, so if f equal to 0, f t equal to 0, then the response will be like this. Initial condition will be there, so this will so this envelope, now here 2 pi by omega d. So this omega d will be omega n 1 minus zeta square. This will call damped natural frequency. So what will happen if you increase the damping? Then so what do you get? What effect do you get in the response? Can anyone tell? If you increase the value of damping, what will happen to this response? Increasing the value of damping, what will happen?
Number of outputs.
Yes, tell me. Bolo.
The time period will increase, like it will take more, like the wave will expand or stretch.
Okay, so if you increase the damping, then what will happen? First of all, this value, if you increase damping, it will be more and more so. Okay, this envelope will squeeze up, and what will happen to this part? So time period will increase. This means that this will be more and more slides, right? Okay, so two things will be observed. One is that the amplitude will decay fast if you increase damping, and second part is that the time period of oscillation will increase. So it will increase more and more. And when omega d or zeta tends to 1, then actually there won't be any time period because this will never be oscillated. Okay. But initially there will be some tendency to oscillation because it will first try to increase with time as time t as t as a option, but eventually it will die down. So that is what is going to happen. That if you decrease the damping, then its frequency will be increasing, the time period will decrease, but at the same time it will persist for a longer time. Okay, so it will be less, the envelope will be less steep, lesser and lesser steep if you increase damping more and more. So that is the observation which will get here. Okay, so this is what we have. Now using this part, actually, let us see this response. Now you see, suppose you consider the response at time t, equal to, let us say, phi by omega d. So t equal to phi by omega d, and then t equal to phi, so t1, t2 phi by omega d plus, let us say, two pi by omega d and so on. So let us consider the response at different time instants. And what are they so special about this time? Because at time t, xt1, this will be a e to the power minus zeta in t1. Okay. xt2 will be what? xt2. This will be a because t2 is more than t1 by amount 2 pi by omega d. So one time period. So that means that this will be equal to e to the power minus zeta omega in t1 plus, let us say, 2 pi by omega d. The other term, cosine term, because cosine at time t equal to t1 by t1 equal to pi by omega d. So this will be 0. Similarly, this will be 2 pi, this will be 4 pi, and so for at time t equal to t2 and t3 and so on. So this will be that one. So similarly t3, this will be equal to a e to the power minus zeta n omega n t1 plus 2 into 2 pi by omega d and so on. Right? Okay. All right. So now what we see, if you plot the value of xt at those instants, that means that what we are doing here is that the response is something like this. Response is actually decaying. And what we are considering is that the function when it is actually the maximum. The cosine value is actually 0. So t1, this is t2, this is t3, this is t4, and so on. So now what we see here is that xt1 is like this. So this will be xt1, xt2 value is like this, xt3 value is like that, and so on. Now what you see from here is that xt2 divided by xt1. What will be the value of xt2 divided by xt1? xt2 divided by xt1. xt1 this you will see that this is e to the power minus zeta omega n 2 pi by omega d. Omega d is equal to omega n minus 1 by zeta square. So this will be equal to, this is equal to e to the power minus omega 2 pi times zeta 1 minus zeta divided by 1 minus zeta square. Okay, and you will see now that xt3 by xt2, xt4 by xt3. So everything, every one of this ratio, this will be equal to e to the power minus 2 pi zeta divided by under root 1 minus zeta square. Okay. So now we see that if you consider the peak, that means when this is in the peak response, then xtn by xtn minus 1, this will be equal to e to the power minus 2 pi zeta divided by 1 minus zeta square. Okay. And these quantities actually, so what we can get from here is that if you take logarithm, the natural logarithm of both sides, then you'll get 2 pi zeta under root 1 minus zeta square. This will be equal to ln of xt n minus 1 by xt n. So now what we see from here, this gives us one way to measure the damping, because this quantity xt n minus 1, so always we are measuring the maximum value of the response whenever it appears. So I'll measure that one, and if you use two consecutive responses, and these two consecutive values, the ratio of these two values, that does not depend upon anything but zeta. So that is very important observation. That is, this quantity, if you plot this quantity by this quantity, or this by that, or this by this, that will depend only on zeta. So this gives us one method to actually estimate the value of damping, because we do not know the value of damping. We have to find out the value of damping. Natural frequency is very easy to find out, because you have to just keep the just get the time period of oscillation. But getting the damping is a very difficult task, and this gives us one way to achieve the to find out the damping ratio. Okay. So what we'll do, we'll measure the responses at different time instance when it reaches the peak, and then we get this ratio for two consecutive values, and from that we calculate using the logarithm the value of zeta. So this gives us actually a kind of quadratic equation which we'll have to solve. Normally, most of the system is actually zeta is so much less than 1, so that the denominator can be neglected. So in most of the cases, if zeta is very small, that is actually our most concern. That is when the damping is low, because that will actually cause more trouble. The damping, low damping, that will cause more trouble. So if let's say we are interested in finding out those systems which will give us more trouble, that means zeta is less than much less than 1. So denominator here can be actually can be safely taken equal to 1. So from that expression, I'll get for this zeta less than 1, I may get zeta. So this will be approximately equal to 2 pi zeta when zeta is much less than 1. So this technique actually is useful for estimating the damping. And this is known as the logarithmic decrement. So x n t n minus 1, and this one, this actually decreases logarithmically. So this is called the logarithmic decrement. Okay. So using this the values of the response at selected time instance, we can actually find out the estimate the value of the damping. Is this clear to you? Is this clear?
Yes, sir. Yes, sir.
Okay, good. Okay, so we now know the natural response, that is xt will have this part. This will be equal to a to the power minus zeta omega n t and cosine omega d t minus pi plus this quantity 1 by m omega d 0 to t e to the power minus zeta omega n t minus tau times sine omega dt t minus tau and f tau d tau. So this will be our response, and we can once you know the value of the function f the force, we can get that eventually. So you see that when time tends to infinity, when it has become very small, very large, then what will happen? This term will actually go out. This is unlike the undamped system where this term was also persisting. Okay. Now what will happen when t tends to infinity? What will happen is that this term, okay, this term will remain. So so xt will be actually 1 by m omega d times m and 0 to. So this term will be zeta omega n t minus tau sine omega d t minus tau f tau d tau. So at time t tends to infinity, so this term will remain because the other term, this will actually go to 0. So this term will be vanishing because of e to the power minus zeta omega n t term, but this term will actually remain. Now with this particular background, we are now able to get the response. At least now we'll consider the steady state response. When the forcing is actually harmonic. So let me call ft equal to f naught e to the power j omega t. Okay, e to the power j omega t. So this is our function. I stress here, I take the complex number e to the power j omega t. But what is actually practical, or what is real? I mean, what really happens is that the forcing is actually a real part of it, or maybe the imaginary part of it. So either real or imaginary part, and accordingly, whatever response we get, I'll have to take either the real part or the imaginary part of the response. So supposing we have f t equal to f naught e to the power j omega t, then the response, what will be the response? There will be a again. So the response will be here, this part, one part will be there, and the other part, this will be f naught divided by m. So what we'll have to do, we have this particular form, 1 by m square plus 2 zeta omega ns plus omega n square, right? What we put here is that we will put, instead of s for the response, the steady state response, I will put j omega. So s will be replaced by j omega. So here we'll have minus j omega square plus 2 zeta omega n, not minus j omega, 2 zeta j omega, and this one is omega n square, and e to the power j omega t. So this will be the response. Now what will happen with time? So when t tends to infinity, what again? So A contains all the initial condition part, A and phi. So all the initial conditions will be actually absorbed in A and phi. And this is the part which is actually only due to force. And what we'll see that when time tends to infinity. So now when we have now, if you take that part, so what we have is that here A e to the power minus zeta omega n t cosine omega dt minus phi. Okay, and here f naught divided by m. Okay, what we get is that 1 divided by omega n square minus omega square plus twice plus j times twice zeta omega n right? And here e to the power j omega t. Okay, so this part will get xt. Now let me erase this quantity. Now a e to the power, this part will be there. Let me again write it down. Theta omega n t cosine omega dt minus pi plus. How do you write down this part? M. Okay. So I can write it down this way. That is, I can put it, so this quantity, I can write down this in the phasor form. That means I can write down it as omega n square minus omega square plus twice zeta omega n square and e to the power I, let us say phi 1, where tan phi 1 equal to 2 zeta omega n divided by omega n square minus omega square. So this is how we can also write down the denominator. Right? So in this form, that is, if I write it down, if I take out this amplitude part, and we can define the phi angle, that tan phi 1 equal to 2 zeta omega n divided by omega n square minus omega square. So in that way, we can actually write it down this way, that is omega n square minus omega square plus 2 zeta omega n square, okay, omega n square under root or half e to the power I phi denominator, so it will be e to the power minus I phi in the numerator, so j omega t minus phi 1. So this will be our response. So please note it down. So this is the total response, where phi 1 equal to tan inverse 2 zeta omega n divided by omega n square minus square. So now what we see is that this part of this response is actually a part which is actually not decaying. So it will be actually periodic function, okay, sine and cosine. But this part of this response is actually a decaying function, you see, e to the power minus zeta omega n t. So what in the response we'll get is that there will be one part of this response. I'll just consider two parts. This part of this response will be, it will go on forever. Okay. It may not start from 0 because it depends upon the phi initial condition, but anyway, so it will be this part. The other part of this response, this one, a to the power minus this thing, so this will be actually, so this will decay. So this part is actually the forcing part, and this part is actually the initial condition. So this part actually takes care of the initial condition, and this part is the forcing part. Now what will happen? The overall response will be actually the summation of these two, because this is just addition. So these are the components. One part is the forcing part, which is actually going all the time. Another part is decaying, which will decay after some time. So the overall response you will get something like this. There will be, well, in the steady state part, there will be this response, that is, this will be there. But beyond, I mean, within this, actually, so something may happen. So this part of this response actually, and this will go on forever. That means this is undecayed. So this part of this response, which will actually be contributed by both forcing and the initial condition. So this part of the response will have two frequencies. These frequencies are either, these distinct frequencies are there. One frequency will be that of the forcing frequency, it is called j omega theta. Another will be the omega theta. So there will be two frequencies present here in this particular initial time instance, and after that, it will one component will gradually go to 0. You see that omega d term, this component will go to 0, and eventually what you'll get after time in very large, so you'll get only the term which is the periodic term which is appearing here. So in this particular response, what you get initially there will be a phase where you won't see any, you may not see any periodicity. Okay. Because there are two frequencies which may not be commensurate. So they may not actually have a single period, because if they are not commensurate, that means if their ratios are not a rational number, then it will. If they are not, then this will not actually have any periodicity. So initially you will see that there is no periodicity, but finally you will get a periodic response. So initial part of the response is called the transient response. Okay. So this part of this response I will call transient response. So transient response is not only due to initial condition. It has also the contribution for the forcing. So transient response is that response which will actually not last for some time, last forever. But what lasts forever is the steady state response. Okay, so I'll stop here. I think we are already on the verge of time, so I'll stop here. So I start from this part. Tomorrow's class, the extra class I'll have. I think from 6 in the evening. That I communicated to you earlier in yesterday's class. So here it is. If you have any problem, you can ask me if you have any doubt. Otherwise, those who are hurrying for the next class, you may kindly leave. If you have any doubt, you can please clarify your doubt now. Next class onwards, I will start from this point. That is where we have the steady state response and the transient part. Okay. If you have any query, kindly let me know. Okay, if no query, then let us stop for today. Okay, we are then meeting tomorrow at 6 p.m. Okay.